Good morning, everyone. I welcome all the participants to session 1 of day 9 on engineering mathematics for GATE aspirants. I welcome all the participants as well as today's speaker, Professor Shwetha H T. A brief introduction about her: she obtained her MSc and MPhil from University of Mysore, and she has got over 7 years of experience in VVCE, and she is expertise in the field of number theory. Currently, she is pursuing PhD under the guidance of Dr. N. Bhaskar sir, who is professor and head of Department of Mathematics in Vidyavadata College of Engineering. And without further ado, let us not
Practice go directly with the session. I request Professor Shwetha H T to take over the session.
Thank you, Kanmani Madam, for the introduction. I welcome everybody to the 9th day of GATE online training. So it is engineering mathematics for GATE. Okay, the syllabus is completely, it includes engineering mathematics. So let us start with the syllabus of the GATE of mathematics. The first one is linear algebra. In linear algebra, we have matrix algebra, a system of linear equations, eigenvalues, and eigenvectors. As I have seen the previous papers, the most of the questions asked based on eigenvalues and eigenvectors, and some of the problems on system of linear equations also. Then the second module or the next topic is actually calculus. In calculus, we have mean value theorems, theorems of integral calculus, evaluation of definite and improper integrals, partial derivatives, maxima and minima, multiple integrals, Fourier series, vector identities, directional derivatives, line integrals, surface integral, volume integral, Stokes theorem, Gauss theorem, divergence theorem, Green's theorem. This is second topic. Next topic is differential equations. In differential equations, we have first order equations, including both linear and non-linear, higher order linear differential equations with constant coefficients, method of variation of parameters, Cauchy's equation, Euler's equation, initial and boundary value problems, partial differential equations, method of separation of variables. Next is complex variables. In complex variables, we have analytic function, Cauchy's integral theorem, Cauchy's integral formula, Taylor series, Lorentz series, residue theorem, and solution integrals. Next module is probability and statistics, sampling theorem, conditional probability, mean, median, mode, standard deviation, random variables, discrete and continuous distribution, Poisson distribution, normal distribution, binomial distribution, mainly completely distribution, correlation analysis, and regression analysis. Last topic is numerical method, error analysis, numerical solution of linear and non-linear algebraic equations, Newton's and Lagrange's polynomial, numerical differentiation, integration by trapezoidal and Simpson's rule, which is nothing but actually numerical integration, single and multi-step methods for first order equation. So this is the syllabus for GATE. Okay, now I'll start with the first topic, which is linear algebra. As I told you, many questions are from linear algebra, that is rank, eigenvalues and eigenvectors, and they are asking system of equations. Okay, so we'll start with the rank of the matrix. So in rank of the matrix, we have minor of a matrix. What do you mean by minor of a matrix? It is the determinant of a square submatrix is called a minor of a matrix. Okay, we have some matrix and we are taking the square submatrix. We are taking the submatrix which is square and we are taking the determinant of that submatrix, and that is called minor of a matrix. If the order of the square submatrix, the above one, okay, if the order of the square submatrix is R, if I take the order as some R, then its determinant is called minor of order R. Okay, I'll take the submatrix. If it is of order some R, you find the determinant that is also called, it is a minor of order R. For example, this is the matrix I have taken, which is 4 cross 3 matrix. In this matrix we have, okay, see in this matrix I'm taking B as a submatrix. Okay, submatrix is nothing but it is deleting some columns and rows. Okay, so here you can see I have taken 2 1 3 1 as a submatrix B. So 2 1 3 1, I'm deleting the third column and third row and fourth row. You can take however you want actually. So 2 1 3 1 is a submatrix of this matrix A, and order of the submatrix it is actually 2. Okay, then we have to find the determinant of the submatrix. So determinant is 2 minus 3, which is 1. So this is called minor of order 2. Order will be same for submatrix and that determinant. Okay, another example, C, I'm taking C is also a submatrix of this matrix A. So just I have deleted the third row. Okay, 2 1 1 3 1 2, first row, second row, and the fourth row, third row is not there. You can delete any row and any column. So that is called the submatrix. So it is a submatrix of order 3. It is 3 cross 3, or we can call it as order 3. Take the determinant of this submatrix, which is C. So when you simplify, you will get the determinant as 8 minus 8. So this is called minor of this matrix of order 3. Okay, order remains the same. You can see the submatrix and also the determinant. The determinant of the submatrix is actually called a minor of order. Here it is 2 and here it is 3. Order of the submatrix will be the order of the minor of the matrix. Okay. Here we have the definition of, now I'll say the definition of rank of a matrix. One of the definition of rank of a matrix is, if A is a matrix, if A be a M cross N matrix, I have taken the general. If this is the matrix, R is said to be a rank of that matrix A if these two condition holds. That is, every R plus 1th order minor of A is 0. Of course, it will not exist. That becomes 0 actually, because R is itself is the rank. So R plus 1th order minor must be equal to 0. Then the next condition is there exists at least one rth order minor. Minor is nothing but we are taking the submatrix of matrix A and we are finding the determinant of that submatrix, that is called actually minor, which is not 0. Okay, the determinant should not be equal to 0. That is rank of A. Rank usually we denote it by a row. Okay, row of the matrix A. That is equals to the order of largest order of the non-zero minor of the A. See, we have a matrix A, you take the largest submatrix. Okay, largest submatrix and you take the determinant, and if that determinant is not equal to 0, then we call it as, that is the minor of the order, and that order will be equal to the rank of the given matrix. Okay, this is applicable, this is useful if it is 2 cross 2 matrix, otherwise no need. Or there is one more definition for the rank of a matrix. The definition is the number of non-zero rows in a row reduced echelon form of a matrix. This is most of the time we use this method instead of the first one. It is the number of non-zero rows. A non-zero row means you take the complete row. If in any matrix, if the complete row is 0, then it is called 0 row. If at least any one of the element is non-zero in one row, then it is called non-zero row. Okay. So the number of non-zero rows in a row reduced echelon form of a matrix. Now, what is echelon form? This is echelon form. I'll give the example for that rank also. So this is echelon form of a matrix. The definition is a matrix is said to be in echelon form if 0 rows, if any, if we have any 0 rows are below non-zero row. Okay, if we have any 0 rows means we should shift it to non-zero rows, or 0 rows come to the last row. Actually, we have to shift it by using row operations. The second condition is the first non-zero entry in any row or in every row must be equal to 1. The first non-zero entry in every row, non-zero row actually must be equal to 1. This is not necessary actually. to make it 1, you have to make it a non-zero element. Why in the definition they will give it as 1 is just to simplify the problem. It is easy if it is, it will turn into like identity matrix that becomes easy to solve further. But anyway, while solving the problems in gate, it is not necessary. You just make the leading entry as non-zero element, and that is more than enough. We can find the rank. Okay, this is called echelon form. Okay, if you have any 0 rows, you shift it to non-zero rows, below non-zero rows, or to the last row. And the first non-zero entry in every non-zero row must be equal to 1 or any non-zero element. Okay, see, this is one of the example. So I have taken some matrix 2 1 0 0 minus 5. Okay, see, this is the leading entry. Okay, in the first row, this is the leading entry and it is non-zero. You don't have to make it 1. If you want to make it 1, you can divide the complete row by 2. So it becomes 1, 1 by 2 and 0 itself. But is of no use, you keep it as it is. Next, you come to the second row. In the second row, this becomes the leading entry, non-zero leading entry. I'm saying the first non-zero entry. So forget about this. This is not a non-zero entry. Now this is the entry. So you don't have to make it 1. You keep it as minus 5 itself. That is fine. Then, now if this is a non-zero element, below that in the same column, elements must be equal to 0. We use the row operations to make it 0. Okay, I'll solve the problem and I'll show you. Anyway, I'll take it as simply example. Here you can see this is already in a row echelon form. Okay, so leading entry is non-zero. In this below that elements are 0. Come to the second row, the non-zero leading entry is minus 5 here. Below that entry is 0. Okay, by using row operations. In the third row, the non-zero entry is 10. And that is the last row, so we don't have to worry. So this is in the echelon form. Okay, this is echelon matrix. Now we have to find the rank. It is easy. So rank is nothing but it is the number of non-zero rows in echelon form. The number of non-zero rows. See, so this is non-zero row because completely it is not 0. If you have 0, 0, 0, it is called 0 row. So it is row 1, 1. Here also we have non-zero elements, so it is 2. Here also we have 10, which is non-zero, so this is also not 0 row. So it is 1 row, 2 row, 3 row. There are 3 rows, so therefore rank of this matrix is equal to 3. So only thing is you have to convert the given matrix into row echelon form or echelon form matrix by using row operations, and the number of non-zero row is equal to rank of that matrix. Another example I have taken, I will tell you directly. So here, the first leading entry is here. I have taken it as 1. Below that entries are 0. Come to the second row, the first leading entry, non-zero entry is 1 here. Below that entry is 0. In the last row, there is no non-zero entry. It is completely 0 row. Okay, so it is in the echelon form now. Now, the number of non-zero rows. Of course, we have non-zero element here. So this is a non-zero row. This is also second row is also non-zero row. You see the third one, which is completely 0, 0. So it is called 0 row. So we have just 2 non-zero rows, this one and this one. So therefore, the rank of this matrix is 2. Okay, it is number of non-zero rows in row-reduced echelon form. You have to use row operations only to convert the given matrix into echelon form of a matrix. Okay, so here I have taken one more example, but this is based on the first definition, which is by using the minor of the matrix. I'll show you one example. To find the rank of the matrix, this is the matrix of order 3, which is 3 cross 3. So how we can do is we have to find the submatrix. The largest submatrix is nothing but it is complete 3 cross 3 matrix itself. I'll take the complete A, and after that you have to find the determinant. You find the determinant. So here the determinant is 181 of this matrix, and it is not equal to 0. If it is not equal to 0, then only we can call it as it is a rank. Okay, so submatrix, I'm taking the same complete matrix because that is the largest submatrix I can take, and take the determinant of that matrix. I'm getting 181, which is not equal to 0. So therefore, we call this determinant as minor. So minor of this, minor of order 3. Okay, because I have taken order 3 itself, the complete submatrix. So it is of order 3, which is not equal to 0. Therefore, rank is equal to 3. Okay, take the largest submatrix, find the determinant. If the determinant is not equal to 0, then the order of that minor is nothing but that is itself a rank. Okay. Here is the problem. Find the rank of the matrix. This is actually a previous exam question paper problem. Find the rank of the matrix A. It is order 4, 4 cross 4. So the first leading entry, you can see it is 1. Okay, anyway, it is non-zero element, so we don't have to worry. And there is no 0 row to shift it to last row or to the below non-zero rows. Okay, so the first leading entry is anyway 1. So below that, I have to make these elements in the same column. We have to make these elements 0 by using the same element, which is leading element, which is row 1, this element. Using this element, make the remaining elements 0 by using only row operations. So here is the condition. This is R2, row 2. So R2 is nothing but it is you multiply 2 here and subtract. So it is R2 minus 2 times of R1. Multiply 2 here and just subtract. You can do 2R1 minus R2 or R2 minus 2R1. Anyway, I want 0 here. Similarly, don't waste time. Do all 3 operations at a time. Next is R3. I want to convert this as 0 by using the same element. Okay. So this is 3. So I'll multiply 3 to row 1. Then 3R1 minus R3 or R3 minus 3R1. So next is I want to make this element also 0. So I'll multiply 6 to row 1. Okay, here I have written wrong. Actually, it is not 4. It should be 6. So you multiply 6 here, then 6 minus 6 gives 0. Okay, so this is what we get. First row remains the same. We are not changing the first row. After using these operations, we get, of course, 2 minus 2 is 0. Then it is R2 minus 2R1, which is 4 minus 2 times of R1 is, it is 4. 4 minus 4 is 0. Similarly, this is 3. 2R1 is, it is 2 into 3 is 6. 3 minus 6 is minus 3. 2 minus 0 is 2. Similarly, use these 2 operations and make the element 0. You can see the leading entry is non-zero, or you can say it as 1. Below that, elements are 0. Okay. Now I'll come to the second row. Okay. Second row, here the leading entry is minus 3. Okay, and below that you have to make this element 0 by using this. But if you do such operation, these 2 remains the same. I don't want these 2 also. So what I'll do is I'll interchange the row R2 with either R3 or with R4. Both are possible. Both are correct actually. So I have interchanged R2 with R3. Just interchange R2, R3. Okay, so this is what we'll get. After interchanging, you can see come to the second row, the leading non-zero element is, now it is minus 4. And below that, now the elements must be equal to 0. So one element is already 0. We have to make this element 0 by using this leading entry. Don't touch the first row, because if you use the first row, these elements becomes non-zero again. Okay, so just take the second row element. Using this element, you have to make these 2 0, but already one is 0. So I'll just make this element 0. So it is, both elements are same, minus 4, minus 4. So we have to just subtract R4 minus R2, or it is R2 minus R4. So after that, I'll get, after doing the operation, not only to that element, I'm talking about R4. So it applies to complete row. Okay, so we'll get 0 here. Now you come to the third row. So after the third row, the first leading non-zero element, you can see it is minus 3. Okay, so below this entry must be equal to 0. Okay, and you have to make this element 0 by using the same element. So elements are same, so just subtract these 2, R3 minus R4 or R4 minus R3, you will get elements as 0, 0. Okay, now you can see this is the last one, which is echelon form. The first leading entry is 1, or it is non-zero. Below the elements are 0. In the second row, non-zero leading entry is minus 4. Below that, elements are 0. In the third row, the first non-zero leading entry is minus 3 here. and below that entry is 0. In the fourth row, there is no non-zero, it is completely 0 row. So this is echelon form. And here the number of non-zero rows. It is 1, 2, and 3. Fourth one is completely zero row. We want only non-zero rows. So the rank of this matrix is equals to 3. 3 is nothing but the number of non-zero rows. Okay, so here is the problem. Another problem. Find the rank of the following matrix. This is also a question paper problem, GATE question paper problem. Okay. You can use any one of the definition, first definition or second definition to find the rank, but second one is actually, it is better to use, which is the echelon form. Okay, if you want, if possible, I'll show both actually. Okay. See, here the first leading entry is 1. Okay, anyway, it is non-zero. Below entry, in the same column, entries must be equal to 0. I want to make these two elements 0 by using the same element. So I'll use the operations, that is R2 is equals to 2R1 minus R2 or R2 minus 2R1. The next operation I'll use here is, it is 4. I have to multiply 4 here. Then 4 minus 4 gives 0. So R3 is 4R1 minus R3 or R3 minus 4R1. So first row remains the same, 1, 1, 0, minus 2. Second row is 2 times of R1. Multiply 2 here and subtract R2. 2 minus 2 is 0. 2 into 1 is 2. 2 minus 0 is 2. 0, 2 into 0, 0. Minus 2 is minus 2. 2 into minus 2, minus 4. Minus 4 minus 2 is minus 6. Okay, then come row 3. Row 3 is multiply 4 to R1 and subtract R3. 4 minus 4 is 0. 4 minus 1 is 3. 0 minus 3 is minus 3. 4 into minus 2 is minus 8. Minus 8 minus 1 is minus 9. Okay, first element is non-zero. Below that entries are 0. Okay, before simplifying, we can see I'll divide the second row by 2. So it becomes 1 minus 1 and it is 3. Okay, I can divide similarly third row by 3. So it becomes 1 minus 1 and 3. Okay, divide by 2 and divide by 3. Or I will write it. Okay. Now, you can see the first element is non-zero. Below that entries are 0. Come to the second row. First leading non-entry is 1. Below that entry must be equal to 0. So using this element only, you have to make this element 0. So operation is actually R3 is equals to, elements are same. So just subtract R2 minus R3 or R3 minus R2. Both are correct. First row remains the same. Second row also we are not touching. You keep it as it is. 1 minus 1 and minus 3 actually. Now R3 is R2 minus R1. 0 minus 0 is 0. 1 minus 1 is 0. Minus 1 minus of minus 1 is also 0. Minus 3 minus of minus 3 becomes plus 3. Plus 3 minus 3 is 0. Okay. So first leading entry is non-zero. Below that entries are 0. Come to the second row. The first non-zero element is 1. Below that entry is 0. The last row is completely 0 row. So this is called echelon form of a matrix. Now we have to find the rank. Rank is nothing but the number of non-zero rows. This is one row which is non-zero. This is second row which is non-zero. This is completely 0 row. So we have only 2. So rank of this matrix is 2. So answer is, the rank of the following matrix is, it is 2. You can use this, or you take the minor of this matrix, largest submatrix, find the determinant. If the determinant is not equal to 0, then the order of that submatrix itself is a rank. Okay, here is another example. This is also a GATE question paper problem. Let A is equals to matrix Aij. I is greater than or equal to 1 and j is less than or equal to 1 with n greater than or equal to 3, which gives the order actually with element is nothing but the condition of the element aij, it is I into j. Okay. Then what is the rank of that matrix? So it matrix looks like this. It is, see, order must be greater than or equal to 3. You can take up to nth order, but I'll take the easy one, which is equal to 3. Okay, so it is A11, A12, A13, A21, A22, A23, A31, A32, and A33. So order is greater than or equal to 3. That is the condition they have given. Easy one is order is 3. Take 3. Then, so each element I into j, the condition is that becomes, function becomes just multiply. Into 1 is 1, 1 into 2 is 2, 1 into 3 is 3. Here it is 2 into 1, which is 2, 2 into 2 is 4, 2 into 3, I into j, 2 into 3 is 6, 3 into 1 is 3, 3 into 2 is 6, 3 into 3 is 9. If you want, you can do for nth order also similarly. Now you find the rank, same condition. After that, if take the first leading entry, below that entries must be equal to 0. So before that, what I can do is, this is R2, I can divide R2 by 2, and I can divide R3 by 3. That makes the problem easier actually. So it is 1, 2, 3. I'll divide by 2, so it becomes 1, 2, 3. Divide the row 3 by 3. So it is a multiple of 3, so I can divide by 3. So it is 1, 2, 3. Okay, that matrix looks like this after simplifying. Okay, now I want to make these two elements 0. Now you do it, R2 minus R1. R2 is equals to R2 minus R1. R3 is R3 minus R1 or R1 minus R3. That gives, first remains the same, first row. Second row is 1 minus 1, 0, 2 minus 2, 0, 3 minus 3, 0. Similarly, row 3 is R3 minus R1, 1 minus 1, 0, 2 minus 2, 0, 3 minus 3, 0. This row is also 0. So first, in the first row, leading entry is 1 or it is non-zero. Below that entries are 0. In the second and third row, there is no leading in non-zero element, or you can say it is completely 0 row. So this is echelon matrix. And now we have to find the rank. Rank is nothing but the number of non-zero rows. And the number of non-zero row is just 1 here. So rank of this matrix is equals to 1. See here we have, so this is equals to 1. Okay, so they have given the order n greater than or equal to 3. Take the least one, which is easy to solve. And each element says it is nothing but I into j, multiply. Make it easy. First you simplify, 2 is common, 3 is common. So I can divide by 2 and 3. And you just subtract the elements. So rank is 1 here. Okay, so these are the few problems on rank. You'll get the same thing. You can either use a row echelon form, or you can find the minor of a matrix to find the rank. So the next is definition is a square matrix A is said to be a singular matrix. It is called singular matrix, the given matrix, if the determinant of that matrix is equal to 0. If the determinant of that matrix is not equal to 0, means we call it as non-singular. Okay, so this is the question paper problem, GATE question paper problem. Which of the following matrices is singular? Singular definition is determinant of the matrix must be equal to 0. So we have to just check which determinant of these matrices equal to 0. So here, if you take the determinant, you take the determinant here, which is 6 minus 5, it is 1. So it is not equal to 0. Find the determinant here. 3 into 3, 9. 9 minus 4 is 5, which is, this is also not equal to 0. Here, 2 into 6, which is 12. 12 minus 12. So here the determinant is equal to 0. We'll see this. 4 into 2 is 8 minus 6 into 3 is 18. So which is minus 10. This is also not equal to 0. So this is the answer. Determinant of this matrix is equal to 0. Such matrix is called actually singular. So answer is C here. Next one. Inverse of a matrix. In the linear algebra, the next topic, other than eigenvalues and eigenvectors, they are asking the questions based on inverse. So the formula to find the inverse of a matrix is, it is A inverse is equals to adjoint of A by determinant of A, or you can write it as 1 over determinant of A into adjoint of A. Next, we have, next definition is transpose of a matrix. So the definition is, if you take A as a matrix, this is of order n, actually m cross n, then A transpose is nothing but, it is A transpose Ij, it is n cross m. A transpose is nothing but, we will write the row in as the columns, just interchange them, where the elements Aij is Aij dash, or the prime is equals to Aj I. Here is the example for transpose of the matrix. A matrix is 1, 2, 3, 4, 5, 6, 7, 8, 9. Its transposes. So first row becomes the first column. 1, 2, 3. That is the first column. 1, 2, 3. Just transpose it. So second row is here. 4, 5, 6. That becomes the second column. 4, 5, 6. Then the third row is here. It is 7, 8, 9. This is the third row. That becomes the third column. 7, 8, 9. If you find, okay, this is called actually transpose. Just convert a row to column. If you find the transpose of this A transpose, you will get A itself. That is the another property actually. A transpose is equals to, we get this matrix A. Okay, this is a very important property. If A is orthogonal, then if the given matrix is orthogonal matrix, then A transpose itself is A inverse. See, if this is a given matrix and if it is orthogonal matrix, then say this is A transpose, it is easy to find. Just convert every row to column, just interchange. Then that A transpose itself becomes the inverse of the given matrix. Instead of finding so much 1 over determinant of A into adjoint of A, if it is orthogonal, you can write directly. Just find the A transpose, and that is itself is inverse. Okay, so we have one problem. This is gate problem. Given the matrices J and K, find the product of transpose of K into J into K. So K transpose means this row becomes, this column becomes row, which is 1. This becomes 1, 2, minus 1. This is K transpose into J is 3, 2, 1, 2, 4, 2, and 1, 2, 6. Multiply them. After that, I'll multiply with K. So it is 1 into 3 is 3. 2 into 2, 4. 4 plus 3 is 7. 1 into minus 1 is minus 1. 7 minus 1 is 6. Then 1 into 2, 2. 2 into 4, 8. 8 plus 2, 10. 10 minus 2 is 8. 1 into 1 is 1. 2 into 2, 4 plus 1 is 5. Minus 1 into 6 minus 6. 5 minus 6 is minus 1. This is the answer. Okay, with this answer, we have to multiply once again K. K is nothing but 1, 2, minus 1. So multiply. 6 into 1 is 6. Plus 8 into 2 is 16. Minus 1 into minus 1 is plus 1. So it is 16 plus 6 is 22. 22 plus 1 is 23. So the product of K transpose J K is nothing but 23. Okay. So here the next question is, for the given orthogonal matrix Q, So this is the given matrix. The inverses. You find the inverse. Okay. You observe here they have given it is as orthogonal matrix. Okay. So when it is orthogonal matrix, we know that A transpose is itself is a inverse. Okay, here if A is orthogonal, then A transpose is equal to A inverse. So we don't have to find A inverse. It is enough to find A transpose. That is nothing but A inverse. You can see here this is orthogonal. So transpose of this matrix is you convert first row into first column. 3 by 7, 2 by 7, 6 by 7, 3 by 7. So 2 by no, this is not the answer. A is not the answer. 3 by 7, 2 by 7, 6 by 7, 3 by 7, 2 by 7. So first row is not the first column. So B is also is not the answer. So here we have 3 by 7, 2 by 7, 6 by 7. Okay. So row changed to column. Second row is minus 6 by 7, 3, 2. Minus 6, 3, 2. Then last row is 2 by 7, 6 by 7, 3 by 7. Here we have 2 by 7, 6 by 7, minus 3 by 7. Third row into third column. Okay. So this is the transpose of this matrix. Since it is orthogonal matrix, A transpose it is itself is A inverse. So answer is actually C. So answer is C. If you want, you can check this one also. Row is 3 by 7, 2 by 7. So it is minus 3. So this is not the answer. This is nothing but this is A transpose. Okay. Q transpose. Sorry, they have given it as Q. C is nothing but this is the transpose. Since it is orthogonal matrix, Q transpose is nothing but Q inverse. So that is the inverse. Instead of finding so much Q inverse everything, if it is orthogonal, do it directly. Next one. The inverse of the matrix order 3 is. So here we have to find the inverse, and this is not the orthogonal matrix. So we have to use the regular method, that is A inverse is equals to 1 over determinant of A into adjoint of A, and we have to simplify. Okay, here it is 2, 3, 4, 4, 3, 1, 1, 2, 4. I'll just do it in the next slide. It is 2, 3, 4, 4, 3, 1, and 1, 2, 4. So this is the given matrix, and A inverse formula is 1 by determinant of A into adjoint A. So determinant of A is, it is 2 into 4 into 3, 12, minus 2, minus 3 into 4 into 4 into 8 minus 3. So this is equals to 12 minus 2 is 10, 10 into 2 is 20, 16 minus 1 is 15, 15 into 3 is 45, minus 45, 8 minus 3 is 5, 5 into 4 is 20. 20 plus 20 is 40, 40 minus 45 is minus 5. So determinant is minus 5, we have to find adjoint A. So adjoint A is nothing but you have to find the minus. So you take this element. So if you take minor of this element is nothing but delete the same row and say column. So you find the determinant of this minus 3, 1, 2, 4. So I will do it directly. 3 into 4 is 12. 12 minus 2 is 10. Then if you take this element, you have to leave the same row and same column. Then the remaining is 4, 1, 1, 4. Don't do it separately. 4 into 4 is 16. 16 minus 1 is 15. but sign is negative. It is plus, plus, minus, plus, minus, plus, minus, plus, minus, plus. Alternative sign starting from plus. Next one, if you take this as the element, leave the same row and same column, remaining is 4, 3, 1, 2. So find out 4 into 2 is 8, 8 minus 3 is 5. So sign is actually plus, plus minus plus. If you take this as the element, leave the same row, same column, the remaining is 3, 4, 2, 4. 3 into 4 is 12, 12 minus 8 is 4. Okay, but here this is plus sign means this is minus, so you just add minus. Then if you take this as the element, leave the same row and same column, then 2 into 4 is 8, 8 minus 4 is 4 and it is positive, minus plus. Next, this element, leave the same column and the row, 2 into 2, 4, 4 minus 1 is 4 minus 3 is 1 and it is minus sign, minus plus minus. Last row, this element, leave this column and row, 3 into 1, 3 minus 12. 3 minus 12 is minus 9. Plus, minus, plus. So plus of minus is minus 9 itself. Take this element, leave this row and column 2 into 1, 2. 4 into 4 is 16. 2 minus 16 is minus 14. So this is plus minus plus. This is plus, this is minus. You have to multiply, you have to add one more minus here. So minus of minus, it becomes plus now. You got minus, we got minus 14 while solving, but in the adjoint formula itself, we will get negative. So minus of minus, it becomes plus. Then the last element is 4. Leave the same column and the row. So 2 into 3 is 6. 6 minus 4 into 3 is 12. 6 minus 12 is, it is minus 12 and this is positive. It is alternative sign plus minus plus, minus plus, minus plus minus. This is plus minus plus. That's all. Okay. After simplifying, you can add these signs if you want. So adjoint is nothing but this transpose. You have to find the transpose, that is the adjoint. So that is equal to, it is transpose. I told you it is nothing but converting row to column. Just 10 minus 15, 5, first row to first column. Then second row is minus 4, 4, 1. This becomes the second column. Third row is minus 9, 14 and minus 12. This is 12. So this is adjoint of A divided by determinant of A is, this is 1 by minus 1 over minus 5. So final answer is like 10 by 5, which is minus 2. I'll write it here. So answer is 10 by minus 5 is minus 2. Minus minus gets cancelled. It is a 4 by 5. Minus 9 minus gets cancelled. It is 9 by 5. 15 by 5 is 3. Minus gets cancelled. It is minus 4 by 5. Minus 14 by 5. 5 minus 5 gets cancelled. It is minus 1. Next term, minus minus gets cancelled. It is 1 by 5. Minus gets cancelled. It is 12 by 5. So this is the answer. Minus 2, 3, minus 1. We will see. Minus 2 plus 3 minus 1. Minus 2 plus 3 minus 1. Here we have this one. One by 5. 4 by 5 minus 4 by 5, 1 by 5. And 9 by 5 minus 14, 12. 9 minus 14, 12. 9 minus 14. Okay, somewhere I think I'm wrong. I don't know. Maybe. Okay, so this is the answer actually. So I think somewhere I'm wrong while solving. Okay, so by using the regular method here, we are finding the inverse, which is the formula is A inverse is equals to 1 by determinant of A into adjoint of A. If it is orthogonal matrix, then we will use A transpose, and A transpose is itself A inverse. Okay, next problem. The matrix P is the inverse of a matrix Q. We have matrix Q and its inverse is nothing but P. Like if this is A, this becomes A inverse. If I denote the identity matrix, which of the following options is correct? Okay. So Q is the matrix and P is its inverse. So we know the property, that is A is the matrix and A inverse is its inverse, then we have the property that A inverse and A inverse A both are equal to I. I is nothing but the identity matrix. This is the property we have. Okay. So instead of A, they have given Q. A inverse is nothing but Q is the matrix, is its inverse is nothing but denoted by P. So I'll take this as P. So A inverse is nothing but P. This is equals to Q. And both are equal to I. This is the property of inverse. But here you see, this is correct. PQ is equals to I, but it is not equal to I, means this is not the answer. In the second one also it is given, it is not equal to I. Third one also, Q into P is not equal to I, means this is also not correct. So all first three are not correct. We'll see the third last one, PQ minus QP. So both are equal to I. You find the difference of these two, QP minus PQ. QP is also I minus PQ is also, both are equal to I. So I minus I, which is equals to 0. Of course, it is equals to 0. This is not equal to identity matrix. 0 is not identity matrix. So answer is fourth one. You can say easily, here they have given both are equal to I. P into Q, Q into P, both are equal to I. Here they have given PQ is I, but QP is not equal to I. PQ is not equal to I, QP is not equal to I. So these three are of course wrong. But here you find the difference of those two. We know that PQ and QP both are equal and and that is equal to I. So we are finding the difference here. When you find the difference, and since both are equal to I, it becomes I minus I. And I minus I is 0. 0 means it is a null matrix, and I means it is identity matrix. Both are not equal. Of course, it is not equal means fourth one is the answer. Next one, if A is 1562 order 2 and B is 3784, then A into B transpose is equal to, A remains the same, 1562, 1562, and B transpose means change row to column. 37 becomes the first column, 84 is the second column. You just find the product. Okay, 1 into 3 is 3, 5 into 7, 35, 35 plus 3 is 38. 1 into 8 is 8, 8 plus 5 into 4, 20, 28. And 6 into 3 is 18, 18 plus 14, 32. Then 8 into 6, 48 plus 4 into 2 is 8, which is 56. 38, 28, 32, 56. Okay, this is the answer. 38, yeah. So keep it A as it is, find the transpose of B, convert the row to column, then you just find the product of those two. Okay. So next topic is, it is eigenvalue and eigenvector, which is very important in GATE. They're asking many questions based on, one is inverse and the second is eigenvalue and eigenvector. Rarely you will see rank finding the rank. So definition of the eigenvalue and eigenvector is, given a square matrix A, it should be a square matrix. If there exists a scalar, real or complex scalar, and a non-zero column matrix X, such that this condition holds. If AX is equal to lambda into X, then this lambda is called an eigenvalue and the corresponding X is called an eigenvector of the given matrix A. Remember, A must be a square matrix. Then there exists a scalar, which is lambda, which is real or complex. Also a non-zero, it must be a column matrix. Okay, non-zero column matrix such that if Ax is equals to lambda x, then lambda is eigenvalue and x is called the corresponding eigenvector. Okay, so that is nothing but Ax is equals to lambda x, or I can write it as A minus lambda I into x. I is nothing but the identity matrix. This is also called as characteristic equation. Okay. Yeah. So you take the determinant here. Determinant of A minus lambda I is equals to 0, which is called characteristic equation, which gives the roots. Roots are nothing but eigenvalues. Okay, we have properties of eigenvalues and eigenvectors. These are very important. If you know these properties, you can solve any one of the problem. Trace of A is equals to sum of the eigenvalues. Trace of A is nothing but if you have, okay, this is some matrix like 1, 2, 3, 4, 5, 6, 7, 8, 9. Trace is nothing but adding these principal diagonal elements. You just add it, and that is same as the sum of the eigenvalues. You will get eigenvalues, and that sum is same as trace of A. This is called trace of A. Then, if A is the given matrix, determinant of A is equals to product of eigenvalues. After simplifying, we will get eigenvalues. Eigenvalues are nothing but the roots of the characteristic equations. Okay, we have equation, find the roots. Those roots are nothing but eigenvalues. So the product of eigenvalues is same as determinant of the given matrix. And sum of the eigenvalues is equals to trace of A. Next property, if one of the eigenvalues is 0, then of course the determinant is equal to 0 because the product of eigenvalue is same as determinant of A. If one of the eigenvalue is 0, then product becomes 0, so determinant of A also becomes 0. So next property is if A is diagonal, means diagonal matrix, or an upper triangular or lower triangular matrix, then the diagonal elements of those matrices are eigenvalues of A. For example, diagonal matrix means it is 1, 0, 0, 0, 2, 0, 0, 0, minus 5. You take this as diagonal matrix. If this is the diagonal matrix, then the eigenvalues of this matrix is nothing but eigenvalue is denoted by lambda. So eigenvalues are 1, 2, minus 5. So diagonal entries are nothing but eigenvalues. Similarly, if it is upper triangular means it is 1, 2, 3, 0. Simply I'm taking some example. Okay, this is called upper triangular. Below the principal diagonal elements are 0. This is called upper triangular. Lower triangular means it's reverse. Okay, above this principal diagonal elements are 0. Anyway, if you have upper triangular and lower triangular matrix, then the diagonal elements of the matrix are eigenvalues. So here the eigenvalues are 1, 5, minus 3. Similarly, in the lower triangular matrix also. Okay, if A is diagonal or upper triangular or lower triangular, please don't simplify by doing so many things by solving the characteristic equation. If you know this property, you can write directly. That is, the diagonal elements are itself eigenvalues. Next property. Eigenvalues of matrix A and A transpose are same. Okay, so if you find the transpose of A and you find the eigenvalue, eigenvalues are same. If lambda is an eigenvalue of matrix A And if determinant of A is not equal to 0, then 1 over lambda is an eigenvalue of A inverse. Okay. Suppose they have given the eigenvalue of A, and the question is to find the eigenvalue of A inverse, means you just check whether the determinant of the given matrix is equal to 0 or not. If it is equal to 0, you have to do it by the regular method. Otherwise, if it is not equal to 0, already we know what are the eigenvalues. Just take the reciprocal 1 over lambda. That becomes the eigenvalue of inverse, A inverse. Next property, eigenvectors corresponding to distinct eigenvalues are always linearly independent. Okay, eigenvectors are nothing but x. Ax is equals to lambda x. So x is called the eigenvectors. So eigenvectors corresponding to distinct eigenvalues are linearly independent. Next property, the eigenvalues of symmetric or Hermitian matrix are always real. Symmetric matrix means this is symmetric. 1, 2, 4, and here also you'll get the same elements 1, 2, 4. Then the second row is 2, minus 3, 0, 2, minus 3, 0, 4, 0, 5, 4, 0, 5. So this is called symmetric matrix. Okay. Hermitian matrix means it is nothing but diagonal elements are real, and if it is 1 plus I, this is 1 minus I, it's conjugate. Here if I take here 2 minus I, that becomes its conjugate is 2 plus I. If I take just the real part 3, of course this is 3 because the imaginary part is 0, so no conjugate exists. So this is called Hermitian matrix. Anyway, the eigenvalues of Hermitian matrix or the symmetric matrix are always real. Next property, the eigenvalues of skew symmetric. I told you now the symmetric matrix. Skew symmetric means it is same, but the diagonal elements are equal to 0, even in a skew Hermitian. Okay, so diagonal elements are 0. Eigenvalues of skew symmetric or skew Hermitian matrix are 0 or purely imaginary. Whereas the eigenvalues of symmetric matrix are real and the eigenvalues of skew symmetric are 0 or it is imaginary. You just check whether the given matrix is real or symmetric or skew symmetric. Based on that, you can find out whether it is real or imaginary. Next property, if lambda is an eigenvalue of orthogonal matrix. Okay. If lambda is an eigenvalue of the orthogonal matrix, then 1 over lambda is also an eigenvalue. If the given matrix is orthogonal matrix, then if lambda is an eigenvalue, then 1 over lambda is also an eigenvalue. Next property, the eigenvalues of orthogonal matrix are of magnitude 1. The eigenvalues of orthogonal or unitary matrix are of magnitude 1. Magnitude is always 1 for orthogonal matrix. Okay, these are the properties. These are very important. If you know this property, you can solve most of the problems directly without solving. Next problem, what are the eigenvalues of, this is the given matrix, you can see this is nothing but lower triangular matrix. Above the principal diagonal elements are 0. This is called lower triangular. So we know the property that if the given matrix is diagonal matrix or upper triangular or lower triangular, then the diagonal elements are itself the eigenvalues. So solution is, since the matrix is lower triangular matrix, the eigenvalues of A are nothing but the diagonal elements. So therefore, the eigenvalues are 6, 3, 7.5, minus 7.2. Instead of solving the finding the characteristic equation and solving it, you do directly. thing is, if it is lower triangular, upper triangular, or if it is diagonal matrix, the diagonal entries are itself eigenvalues. Next question. One of the eigenvalues of A, matrix A, is equals to 5, 6, 2, 3, 5, 9, 2, 1, minus 7 is 0. One of the eigenvalues of this matrix is 0. Lambda is equals to 0. Is A invertible? Solution. So they have given one of the eigenvalue is 0. So I'll take one value as 0. So this is an eigenvalue of the given matrix. That implies invertible, because here I told you the property. Properties of eigenvalues and eigenvectors. Okay. See, this property, determinant of A is equals to product of the eigenvalues. Here in the problem they have given one eigenvalue is 0, means when you find the product, so determinant of A becomes 0. Okay. Here determinant of A is 0, and we know that if determinant of A is 0 means it is singular. So the given matrix is invertible, or we can find the inverse. If determinant of A is not equal to 0, that is called non-singular. If the given matrix is not singular, then only A inverse exists, or A is or the given matrix is invertible. But here in this problem, determinant is equal to 0 because one of the eigenvalue is 0. Determinant is equals to product of the eigenvalue. Since one of the value is 0, so product becomes 0, and that is equals to determinant of A. Since it is 0, it is singular, so it is not invertible. We cannot find the inverse. Next problem. Consider the matrix 5, minus 1, 4, 1. Which one of the following statements is true for the eigenvalues and eigenvectors of the matrix? Okay, so here they have given eigenvalue 3 has a multiplicity of 2 and only one independent eigenvector exists. Eigenvalue 3 has, okay, anyway, we'll before finding, we'll find out what are the eigenvalues and eigenvectors. I'll do it in the next slide. Okay, the given matrix is 5, minus 1, 4, 1. Okay, to find the eigenvalues and the eigenvectors, we want characteristic equation. So, okay, this is the important trick. You can find the characteristic equation directly instead of doing all this. Determinant of A minus lambda I is equals to 0, where A is this one, I is nothing but the identity matrix. Since it is order 2, identity matrix becomes 1, 0, 0, 1. After that, we have to multiply lambda. It becomes lambda into I, which becomes lambda 0, 0, lambda. Then we have to find the difference, and you have to solve that. That gives the characteristic equation. Instead of doing that, if it is 2 cross 2, the easiest method to find the characteristic equation is, it gives actually quadratic equation. It starts from lambda square. Okay, then it is alternative sign. First term is always plus, now it is minus, then it is sigma d, or we can call it as trace. Okay, d denotes the diagonal element, sum of the diagonal element into lambda square, or 1 into lambda square. First term is positive, now it is alternative sign minus, it is sum of the diagonal element of the trace into lambda, alternative sign minus becomes plus, determinant of A is equals to 0. This is easy to find instead of doing so much. Now I'll find out the equation of this matrix, lambda square minus Sum of the diagonal element is nothing but diagonal elements are 5 and 1. Sum is 6. So 6 lambda. Plus you find the determinant. Determinant is 5 minus of minus 4, which is plus 4. 5 plus 4 is 9. So this is the equation. Instead of doing so much, you can do directly. Remember this formula. This is lambda square minus sigma d, which denotes the sum of the diagonal elements into lambda plus determinant of A. Plus minus plus, it is alternative sign equal to 0. Now you simplify this equation, that gives the roots. So this is nothing but it is of lambda minus 3 whole square. A minus b whole square, you expand it, lambda square plus 9 minus 2ab is minus 6 lambda. So I can write this expression as lambda minus 3 whole square is equals to 0, or lambda is equals to plus or minus 3. No, sorry. Therefore, lambda is equals to 3, 3. Okay. Eigenvalues are 3 and 3. So I'll go back to the problem now. Okay. See, consider this matrix. Which one of the following statement is true for the eigenvalues and the eigenvector of the matrix? Eigenvalue 3. So we are getting eigenvalues 3, of course. See, the eigenvalues are 3. Eigenvalue 3 has a multiplicity of 2. Of course. See, whole square, it is 2. Multiplicity of 2 and 1. Okay, this is correct actually. We have to check now the eigenvector. And only one independent eigenvector exists. We have to check whether we are getting only one. Here also second one, eigenvalue 3 has a multiplicity of 2. Of course, it is correct, which is 3, 3 and 2 independent eigenvectors. Third one is eigenvalue 3 has multiplicity of 2. This is also correct. And no independent eigenvector. Last one, eigenvalues are 3 and minus 3. No, this is not correct because we are getting eigenvalues as 3 and 3. So fourth one is not the answer. We have to check these 3 now. So we'll find out the eigenvectors now. To find the eigenvectors, it is okay. So this is the given matrix. We get 5 minus lambda. You have to find A minus lambda I of x is equals to 0 to find the eigenvector. A minus lambda I is nothing but always diagonal element minus lambda, that's all. It is 5 minus lambda minus 1, 4, and diagonal element is 1, so 1 minus lambda into x is nothing but you can take xy or anything, x, y is equals to 0, 0. So you solve these two. When you simplify, you will get the equations 5 minus lambda into x minus 1 into y is minus y is equals to 0. 4 into x plus 1 minus lambda into y is equals to 0. Okay. This is called the equation. Now we have lambda values. Substitute here and you simplify. So okay, substitute lambda is both the values here. So lambda is 3, 5 minus 3 is 2. So it is 2x minus y is equals to 0. Next, 4x plus lambda is 3, 1 minus 3 is minus 2, so it becomes minus 2. Plus of minus is minus 2y is equals to 0. In equation 2, I can divide by 2, 2 is common, so it becomes, first equation I'll write it as it is, 2x minus y is equals to 0. Here you can divide by 2, so it becomes 2x minus y is equals to 0. You observe these two equations are same, they are one and the same. So you are getting the only one equation, or if you solve both, you will get the same answer. It is of no use. So only one equation, 2x minus y is equals to 0, or 2x is equals to y. You just cross multiply the coefficients. It is x by, here the coefficient is 1, 1, that is equals to y by coefficient of x is 2. Okay, and we equate it to some constant k to find the values of x and y. Instead of equating to some constant k, make it easy, equate it to 1, because 1 is also a constant, because k gets cancelled finally somehow. So I'll just equate it to 1 because 1 is also constant. Equate 1 by 1. X by 1 is equals to 1, or x is equals to 1 into 1 is 1. So x is equals to 1. Y is equals to, y by 2 is equals to 1, or y is equals to 2 into 1 is 2. So y is equals to 2. So we are getting only one eigenvector since both the equations are same. If you take another value also, you will get the same equations because it is one and the same. So answer is, of course, eigenvalue is 3 and has a multiplicity of 2. These 3 are correct. They are half of it. And only one independent eigenvector exists. Of course, this is correct. This is the answer. Second one is 3 has a multiplicity of 2. Of course, it is 3, 3 we are getting. 2 independent eigenvectors. No, we got only one independent. So this is not the answer. Eigenvalue 3 has multiplicity of 2 and no independent eigenvector. No, we are getting independent vector or eigenvector, sorry. So third one is not the answer. And fourth one, already I told you, this is not the answer because they are saying that 3 and minus 3 are the eigenvalues, but we are getting 3, 3 are as the eigenvalues. So answer is first one. Similarly, I forgot to tell you here. Okay, I'll write it here itself. So if it is matrix 2 cross 2 or order 2, the equation to find the characteristic equation is, it is lambda square minus sigma d, which is sum of the diagonal elements, into lambda plus determinant of a is equals to 0 for order 2. If it is 3 cross 3 or order 3, then it is lambda cube minus sum of the diagonal elements into lambda square plus it is sum of the minors of the given matrix into lambda minus determinant of A is equals to 0. It is alternative sign. Since order is 3, it is cubic equation. It starts from cube, from 3, lambda cube, and it is alternative sign plus minus. Lambda cube minus sum of the diagonal elements into lambda square plus sum of the minus of for the given matrix into lambda minus determinant of A is equals to 0. So next question, consider the following simultaneous equations. These are the equations with C1 and C2 being constants. C1, C2 are constants here. The characteristic equation for these simultaneous equation is, we have to find the characteristic equation. That is what I told you now. So I'll just take the coefficients now for this one simultaneous equation. I can write this as 3, 2, 4, coefficient is 1. Okay. And here they have given x1, x2. I'll take it as x1, x2. We can, okay, this is equals to C1, C2. This representation is nothing but AX is equals to B. We can convert equations into matrix or matrix into equation by using this expression. A is nothing but this is the matrix, X is nothing but the unknowns, matrix B is the right hand side. Okay, if you multiply, you will get the same thing once again. Now we have to find the characteristic equation. Okay, you just take this matrix 3, 2, 4, 1. Now you find out the characteristic equation directly by using that formula. That is nothing but, since it is order 2, it is start from lambda square, then it is alternative sign, it is minus sigma d, or nothing but sum of the diagonal elements. So sum of this diagonal elements are 3 and 1, so sum is 4. 4 into, write lambda as it is, alternative sign, it is plus, find the determinant of this matrix. Determinant is, it is 3 into 1 is 3 minus 4 into 2 is 8. So 3 minus 8 is minus 5. So it is minus 5 equal to 0. Or I can write this as lambda square minus 4 lambda plus of minus is minus 5 is equals to 0. Okay, so this is the answer, first one. Lambda square minus 4 lambda minus 5 is equals to 0. Okay, so use this method and find out directly. Otherwise, you have to use the regular formula, which is determinant of a minus lambda I is equals to 0. You have to simplify and you have to find the expression or the equation or do directly. Lambda square minus sum of the diagonal elements plus determinant of a is equals to 0. So answer is A, first one. Okay. This is the given problem. Find the sum of the eigenvalues of the matrix. So this is the matrix. You have to find the sum of the eigenvalues. Okay. So first we have to find the eigenvalues and then we have to find the sum of it. How can you find the sum? See, there is the property says that sum of the eigenvalues is equal to trace of the matrix. Here is the property, I'll show you. Okay. First property, sum of the eigenvalues. Sum of the eigenvalues is equals to trace of A. So trace of A is nothing but, using this property, I can solve the problem directly. Okay. So we know that now sum of the eigenvalue is equals to trace. Trace is nothing but diagonal elements. This one, this is called trace. Okay. So since trace of, if you take this as the matrix A, if trace of A is equals to sum of the eigenvalues, you just add them. So it is 215 plus 150 plus 550. So sum is 5, 10, 11, 5, 7, 8, 9. Okay, it is 915. So first one is the answer. So if you don't know the property, you have to find the characteristic equation first. Then when you solve the characteristic equation, you will get the eigenvalues and you have to find the sum. Or if you know the property, you can do it directly. Sum of the eigenvalues are equal to trace of the given matrix. So this is the trace of the given matrix. Just find the sum and that is the answer. Okay. Next question. If the entries in each column of a square matrix, it is a square matrix, and entries in each column, if the entries in each column of a square matrix M add up to 1, then an eigenvalue of M is. Okay. We have some column square matrix. So better I'll take 3 cross 3. Order 3. Okay. I'll take 3 cross 3 matrix. I'll take it as matrix M. If the entries in each column add up to 1. So when you add the elements of those that square matrix, sum must be equal to 1. So it is nothing but, of course, identity matrix. So 1, 0, 0. So this is first column. You add the elements 1 plus 0 plus 1. So sum is equals to 1. Take the next column. It is 0, 1, 0. So sum is 1. Last one 0, 0, 1. Sum is 0. Sorry, sum is 1. Okay. It is a square matrix. So for example, I have taken order 3, 3 cross 3. And if you add the entries in each column, sum you will get it as 1. So here sum is 1. Here also sum is 1. Sum of this column is 1. So we have such matrix. You have to find out the matrix first. Then eigenvalue of this matrix is, what is the eigenvalue? I told you the property once again. Eigenvalues of diagonal matrix or upper triangular matrix or lower triangular matrix, that is nothing but the diagonal elements itself. Okay. Therefore, eigenvalue of m is, it is 1. Okay. If the entries in each column of a square matrix, take some square matrix, and if they add up to 1 means you add every elements of the column, sum must be equal to 1. So it is of course identity matrix. Then an eigenvalue of m, it is nothing but it is diagonal element, so it is equal to 1. Next problem. Okay. The matrix 2 minus 4 and 4 minus 2 has real eigenvalues and eigenvectors, real eigenvalues and real eigenvectors, real eigenvalues but complex eigenvectors, complex eigenvalues but real eigenvectors, complex eigenvalues and eigenvectors. So we have to simplify to see whether it is real or complex. Okay, it is 2 minus 4, 4 minus 2. You see, first you observe this is not a symmetric and it is not skew symmetric also. If it is symmetric matrix, we can say directly that the given eigenvalues are real. If it is skew symmetric, eigenvalues are 0 or it is imaginary. It is neither symmetric nor skew symmetric. So we have to simplify by using the regular method. Two minus 4, 4 minus 2. Okay, if this is the matrix, we have to find the eigenvalues. So first I'll find out the characteristic equation, which is lambda square minus sum of the diagonal elements. Okay, 2 minus 2 is 0, so 0 lambda, or you don't have to write it, plus determinant of this matrix is 2 into minus 2 is minus 4, minus 4 into 4 is minus 16, so it becomes plus 16, which is plus 12. So 12 is equals to 0, or I can write it as lambda square plus 12 is equals to 0, or lambda square is minus 12, or lambda is equals to plus or minus root of minus 12, which is nothing but root of minus 1 is I, imaginary. So it is I into root 12, or you can write it as plus or minus I. Root 12 can be written as root of 4 into 3, that is 2 root 3. Anyway, this or this. Anyway, you can see here it is I. So it is, of course, imaginary. Eigenvalues are, you see here, they have given the first two options as real eigenvalues. So it is not the answer. Eigenvalues are complex. So this is not the answer. We have complex eigenvalues, but real eigenvectors, complex eigenvalues and complex eigenvector. We have to check eigenvector now. So to find the eigenvector, you have to find this equation, that is A minus lambda I of x is equals to 0. A minus lambda is nothing but 2 minus lambda into x minus 4y is equals to 0. Second equation becomes 4x minus 4x plus minus 2 minus lambda of y is equals to 0. This is matrix A. Lambda, write it as it is. I is nothing but identity matrix. Since it is order 2, I becomes 1, 0, 0, 1. Simplify it. X nothing but it is unknown matrix. You can take it as xy or x1, x2 is equals to 0, 0. Simplify, you will get equation like this. Then eigenvalue, I'll take any one of the eigenvalue, put lambda is equals to plus I2 root 3. Okay, I'll substitute here 2 minus lambda, I'll take it as first one, plus I2 root 3 into x minus 4y is equals to 0. I can take 2 common, 2 of 1 minus I root 3 of x minus 4y is equals to 0. We can divide by 2. So it is 1 minus I root 3 into x minus 2y is equals to 0. Or if you shift it minus 2y to that side, it becomes plus 2y. Okay, just cross multiply the coefficients. It is x by 2 is equals to y by 1 minus I root 3. Okay, so equate it to some constant and find the values of x and y. X is equals to, you compare with these two, x by 2 is equals to 1 or x is equals to 2. Y by this is equals to 1 or y is equals to 1 minus I root 3. You can see here we are getting the complex. So eigenvalue is also complex. So answer is, okay. We are getting eigenvalues, complex eigenvalues. But here the third one is a real eigenvector. So we are not getting real, we are getting complex. So third one is also, this is not the answer. This is the answer. We are getting complex eigenvalue and the complex eigenvector for this matrix. Okay. So please remember the properties. It is very important and it is very easy to solve the problems in GATE. Otherwise, you have to do the lengthy procedure, the regular method of mathematics to solve the problems. Okay. So there are plenty of problems. Anyway, I'll stop now. Thank you one and all. In the next session, I will continue. Over to you, ma'am.
Thank you, ma'am. I thank all the participants for the patient listening, and I thank Professor Shwetha H T for her detailed and fast-tracking tips for our students. And I request all of you to fill the feedback form that is there currently in your live chat box. After the session, it will be available for you in the chat box only. And I request all of you to attain our next session on day 10, that is 7th December, that's next Monday. Session 1 will be water quality treatment by Professor Shilpa B.S. and second session will be on fluid mechanics and hydraulics by Professor D.P. Mahesh sir. I request all of you to join in our next session, and I thank all the participants for their active participation. Thank you.